Going to talk about problem 18.24, page 74, volume 3. I like to call this problem M311 in August at 2 p.m. If you've had to sit in that classroom at that time, certainly a year or two ago, you know what I'm talking about. Hot, hot, hot classroom. Okay, imagine you have 50 students in the room. Assume each student has normal body temperature 37, all right? Room temperature held at 22 by the air conditioning, and each student has a surface area of about 2 meters squared, emissivity of 0.7. All right, these are assumptions. They might not be perfect, but at least it gets us started thinking about this type of situation, right? Is your skin exactly 37 everywhere? Probably not, but okay, anyways. Yeah, all right, so what is the energy radiated per second by a single student? So if we're trying to do that, if you want to try to do it yourself, go ahead, pause the video. I'm going to do it right now. Power, that's what we're looking for. Energy per second is power. And that's sigma A E T of the student to the fourth power. Does that show up? Yeah, good enough. All right. Now, in this case, we kind of have all the information. Sigma is the Stefan Boltzmann constant. What is that? 5.67. Is that right? I'm going to make sure I don't screw this up. Where is that number? It's probably on the back of the book. Oh my gosh, is it? Yes, 5.67. And then the units are watts per meter squared per Kelvin fourth. All right. Area, that's our 2.0 meters squared. Emissivity, that's what this 0.7 is. And then temperature to the fourth. You do not use 37. This is T, not delta T. We've got to get this into Kelvin. So that ends up being what? 310.15 Kelvin. So that's the temperature you got to plug in. So that's one of the things you got to watch out for. And out of all of that, let's see, I got the number here somewhere. You can punch it in. Let me see what I've got here for that number. What was it? 734. Quick note on sig figs. I think it was 734.5. Maybe that's what it was. Maybe I'll write that right here. Now, a note on sig figs. Generally speaking, right, a lot of these numbers, especially the emissivity, that's a very crude estimate. So we're probably only right to 1 sig fig here. On a test day, just follow the same rules. Assume everything is good to 3 sig figs and write your answer to 3 sig figs. But yeah. So I don't want to waste your time tracking sig figs on exam questions if I can avoid that. We'll do that in lab. But so if I was writing this problem, if that's what I got, I would probably write on my test 735 watts. Or you could write it like this. Either one of those would be full credit on test day, right? But our default is to round your final answer to 3 sig figs. Now, it's important to keep the unrounded answer in case we need that for the next part, maybe, but. All right, so let's get to the next part. The net energy radiated to the room by all the students during a 1-hour lecture, assuming these parameters are true. If you want to try and do it yourself, go for it. I'm going to start now. If we want the net energy radiated to the room, I'm going to start by getting the power. And remember, this is change in energy over change in time. So if I multiply this by the change in time on both sides, that will get me the net energy radiated to the room by a single student. And then if I multiply by n on each side, that should get me the net energy radiated to the room by all students in 1 hour. Now in this case, sigma, A, and E are the same. Now what's going on here? What's happening is the students are radiating energy off their body, but there's also incident radiation from the room coming into their bodies. And so unless you're in space with temperatures near absolute zero, right, the energy that you absorb is not negligible, right? You're absorbing energy just like you're emitting energy through radiation. So now in this case, we could look at this situation here, and we know sigma, we know A, we know E. The temperature of the students, that we know we have to use 310.15 Kelvin. And you might be saying, well, the room's a lot cooler. Actually, when you look at it, let's see, it's 22. So if we add 22 plus 273.15 for the room, what is that? 295.15 Kelvin. They're actually pretty close. Now, be careful. Be careful. When you plug in the numbers, you can't just subtract the temperatures and raise that to the fourth. So you can't do T students minus T room, then raise it to the fourth. That doesn't work. Okay? Yeah, it'd be nice, it's easier, but it's wrong. Okay, so, and when you punch that in, don't forget, power, the units are joules per second. So we're gonna have to use 3,600 seconds here. And then N is the number of students, that's 50. And when I punch all that in, I got, what did I get? 23 millijoules or something like that, or 23 megajoules, excuse me. Again, off in the first sig fig. Interestingly enough, you could do this as 6.6 kilowatt hours. All right, so you can actually take the power, right, and get the power in watts, convert it to kilowatts, and then just multiply by an hour and by 50. But then you could have units of kilowatt hours, right? That's a unit of energy, power times time. All right, and I think, and then one last question is, in that room, the AC is never good enough, right? So what's gonna happen to this actual number over time? Well, let's think about it. How much energy are the students radiating if the air conditioning is insufficient? Is this an overestimate or an underestimate? Pause the video if you want to think about that. All right. Well, look, if the AC is insufficient, the room temperature should heat up a little bit. If the room temperature heats up, we're going to radiate less power. So as the room gets hotter and hotter, you're emitting less and less energy. But, oh my gosh, the room's already getting hotter and hotter and it's unbearable in there. So, all right, so that's all I wanted you to think about. In practice, these problems look like you only have one sig fig, but on test questions, right? 3, watch out for your temperatures, get them in Kelvin. Watch out, you can't do this. You have to do temperature of the fourth minus temperature of the fourth. And remember that we sometimes go back and forth. Sometimes we'll talk about energy per second, which is power, or sometimes we'll talk about energy, which is power times time. Those are the main ways I mix these problems up. They usually sound really complicated, but in the end, the process is very straightforward for almost all of these types of problems. And again, the number is not necessarily hugely trustworthy, but yeah,